This is the chemistry behind the atomic bomb. An isotope is defined as a element that has two or more different forms of the element. Normally, elements have the same number of protons and neutrons in the nucleus, but isotopes have the same number of protons with different number of neutrons. This leads to having a different atomic mass. A radioactive isotope is the most unstable form of an isotope, and there are 50 radioisotopes that are found in nature, while there are over 1,000 known radioactive isotopes of elements that can be produced artificially. As time passes, a radioactive isotope loses particles and therefore releases energy. While we don't know which atom will decay, we do know that the decay will happen at the same rate. The amount of time for half of the isotope atoms to decay is known as the half-life. Different isotopes can have different half-lives, and therefore the time to decay is different for each isotope. The half-life of uranium-235 is 700 million years, while the half-life of uranium-238 is 4.5 billion years. If one neutron from uranium-235 strikes another nucleus, it will cause fission, a process of radioactive splitting where the nucleus of one atom is split into smaller and lighter nuclei. The chain reaction will then continue to spread to other atoms. If a reaction is able to sustain itself, the reaction is considered critical and has achieved critical mass. Critical mass is the amount of fissile material needed to cause a sustained nuclear chain reaction. Natural uranium is found containing 99.284% of the isotope uranium-238. Uranium-235 makes up 0.711% of the mass of natural uranium. As uranium-238 can absorb a neutron, it will not undergo fission as it is able to absorb the neutron, and it will not sustain a nuclear chain reaction that is required to release the explosive amount of force. In order to create the runaway nuclear chain reaction needed for an atomic bomb, enriched uranium is needed. Techniques to enrich the uranium can be gaseous diffusion and gas centrifugation. The process of gaseous diffusion forces gaseous uranium hexafluorine through a semi-permeable membrane which separates the molecules of uranium-235 and uranium-238. Gas centrifugation uses rotating cylinders that create strong centripetal forces, which forces the gaseous uranium-238 to the outside of the cylinder, while the lighter uranium-235 collects near the center of the centrifuge. Currently, gas centrifugation produces nearly 100% of the world's enriched uranium. If uranium-235 absorbs a neutron, it will split into two new atoms which release both energy and three new neutrons. If these newly released neutrons are absorbed by other uranium-235 atoms, it will continue to release energy and neutrons. This cycle will repeat itself until it becomes self-sustained and until all the uranium-235 atoms are split. The amount of energy released leads to a sudden explosive release of energy. A nuclear weapon chain reaction is started by bringing the uranium-235 into its supercritical state very rapidly, although it is possible that the device can undergo a spontaneous fusion causing a fissile where the material is blown apart before complete fission can happen. The atomic bomb Little Boy was a gun type of atomic bomb and used 56 kilograms of 80% enriched uranium-235. A gun-type atomic bomb is split into two parts, the projectile and the target. The design used a conventional chemical explosion to send a hollow subcritical bullet into a solid sphere of supercritical mass of uranium, which initiated the nuclear chain reaction. The bullet was made up of 60% of the total fissile mass, while the sphere target was made up of 40% of the total fissile mass. When Little Boy detonated, only 0.6 grams of its mass underwent nuclear fission, which transformed into energy, most notably kinetic heat and radiation.